So this lesson is applications of linear equations. We're going to be using the same equations that we utilized on the previous lesson, but these are going to be story problems. So you really have to watch your labels, and you have to watch what information you're given, and it won't outright tell you things like this is your y-intercept or this is your slope. You have to kind of read between the lines on these questions. So anytime they say rate of change, that's key phrase for slope. And anytime it says starts at or begins at, that's a y-intercept, because a starting point is the y-intercept of the line, right? It's when time is 0. So t, time, x, they're all kind of interchangeable here today. Just be careful. So in this first example, in 2004, a school population was 1,001. And then by 2008, the population had grown to 1,697. Assume the population is changing linearly. And then it says how much did the population grow between 2004 and 2008? Well, that's just a simple subtraction problem. So if we subtracted those two numbers, we get 696, I believe, students. And then how long did that population take to change from 1001 to 1697? Well, that would be from 2004 to 2008, so that would be 4 years. So that's leading you up to this next question, which is, what is the average growth rate per year? This is fancy talk for slope. So it's change in students over change in years. So 696 students per 4 years. And if we reduce that, it comes out to a nice 174 students per year. So labels are super duper duper important here. What was the population in the year 2000? Well, they didn't tell me that, but I can maybe figure that out by going backwards. So you can either create an equation and use your equation at this point, or you can just literally think backwards. So if you started with 1001 in year 2004, and every year you're supposed to be growing 174, well, if you go backwards in time, that means you have to subtract 174. And how many times did we subtract it? Well, from 2004 back to the year 2000, so we subtracted 4 times. So doing that on my calculator, because yeah, my brain is done, looks like we had 305 students in 2000. So that's this answer right here. And now it says find an equation, and then we're going to have to use the equation after that. So this is part D, here's part E. So I have, they want me to start in the year 2000 as like my starting point in time. So what that means is we can measure time starting in the year 2000. So t equals 0 is the year 2000. So what we're going to be writing here is P, because they want me to use P right here, equals slope, which we said was 174. And they want me to use T. Got to watch your variables if they define them. And then in the year 2000, we started with 305 students. So that was your, quote, starting point, which we know is the y-intercept of a graph. But that's how you have to kind of interpret. These questions are all over the SAT test. So you have to recognize that this number here is the starting value, and this number here is your rate of change per year or per time value. Now it says use your equation to predict the population in 2011. So remember, if your population growth is starting in the year 2000, when you get to 2011, that's 11 years later. So when t equals 11 is what we're going to be calculating. So using our equation, 174 times 11 plus 305. Looks like I already calculated this, so it comes out to 2,219 students. And sometimes students fight with their teachers on this because they're like, well, why do I have to come up with an equation? Because I could just keep adding 174, how many times I want. Well, that's true, but the whole point of algebra is to be able to program machines, and machines think very logically, and you want them to work efficiently. So this is kind of the basis of computer programming, so we got to keep going, thinking like a computer. Somebody has to program them, right? All right, next question. Phone company has a monthly cellular plan where customers pay a flat monthly fee, so that's like our starting point. and then a charge per minute. So that would be slope. So first they're going to give us some clues. It says if a customer uses 410 minutes, the monthly cost will be $71.50. So that's like an ordered pair in its own. And then another customer, or maybe the same one in another month, 720 minutes, the cost is $118. So it says find the linear equation where x is the number of minutes used. So here's what I'm going to do. I'm going to write those two clues out as ordered pairs. So 410 minutes, the charge was $71.50. And then 720 minutes, the charge was $118. So I'm going to need to calculate slope. Lovely. y2 minus y1 over x2 minus x1. And remember, we talked about slope as being the charge per minute. So when I calculate this, it should, I mean, you guys don't pay per minute anymore on cell phones, but it shouldn't be anything crazy. And it comes out to 0.15. So 15 cents per minute is what they're going to charge you. This is how we used to do cell phones back in the day, huh? And then we are going to need to come up with an equation. So I have two ordered pairs here. I'm just going to go ahead and use point slope form. Looks like we can use y and x because they didn't define anything else. So let's say y minus, this is my favorite point today, so I'm going to use that. Y minus the y coordinate equals slope, and then times x minus the x coordinate. All right. I'm going to clean this one up a bit. Let's see here. If I distribute the 0.15 and then I add the 118 over, so let's see here. That'd be 0.15x, so 0.15 times 720, so negative whatever, and then plus 118, that comes out to plus 10. So that is the answer to part A. For part B, it says interpret the slope and the vertical intercept, or the y-intercept. So the slope, remember, was money per minute. So this is 15 cents. Oh, I shouldn't label it that way. Let's go back. So we're going to charge, I need to write this somewhere though. So each minute costs 15 cents, or you could write it with a dollar sign with 0.15. And the flat monthly charge is $10. Probably a bargain, right? Probably not. You guys spend too many minutes on your phone. All right. And then it says use your equation to find the total monthly cost if they had 687 minutes. So we're going to use that clue. That's going to go in for x into my equation, or right there. So 0.15 times 687, and then plus 10. So that customer is going to be charged $113.05. It seems like a lot. They didn't even talk about data yet. All right. So there's that example, and there's one like that on your test, I think, so you might want to revisit that. Oh, moose. Who doesn't love a nice Canadian moose? All right. The moose population in 1991 was 4,360. By 1999, it's now 5,880. Apparently the moose are bored. The moose population is growing. That's good. What's the formula to find the population? Use P. So the ordered pairs, if you want to think of it that way, so I don't ever want to use the actual calendar date. I feel like that's just a bad idea. So what I'm going to do is I am going to say we're going to measure from 1990 because that would be easy for me. So I'm going to say that t equals 0 is the year 1990. So this year right here would be 1. So 1 year, the population is 4,360. And then in 1999, that'd be 9 years later, what do you have here? 5880. So let's find slope first. 5880 minus 43, 60. And that happened in 8 years. So calculating that, looks like the moose population is growing 190 moose per year. Okay, so there's slope. And then I do need the beginning value, or how many moose were there in 1990. So you can actually go find the actual formula that way. You can use point slope form, or you could just back it up. So for 360, if you back up 1 year, you're going to lose those 190 moose. Turns out that comes out to, let's see, 4170 moose. So we started with that many moose in 1990. Not the only way to get that part of the equation. And I actually haven't written the equation yet. So the population is growing at a rate of 190. I'm going to say T. And then we started with 4170 moose starting in the year 1990. Now, at no point did they actually tell me I had to start in the year 1990. That was just kind of something I chose. You could have started in 1991. But what's going to happen is on this next part of the question, part B, no matter what your formula is, if it's accurate, you're going to get the same answer as me right here. What does your model predict the moose population will be in 2003? So if I started in 1990 all the way up to 2003, we are talking 13 years later. So I'm going to use T equals 13. I'll plug that in right there. And looks like we have 6,640 moose. Very good. All right. These can get complicated if you're not as familiar with the formulas, right? Let's say, we're going to have to do the next two. I was going to try to skip out on some time, but I don't feel good doing that. All right, the Federal Helium Reserve says that there's 16 billion cubic feet of helium in 2010. Okie dokie. And it's being depleted by 2.1 billion cubic feet per year. So that last clue, that is slope. But remember, the word depleted means that it's decreasing. So it's decreasing 2.1 billion cubic feet. What we're going to do is another math trick where we're going to leave off the billions and we're just going to say, P.S. all this is in terms of billions. So that way we don't have crazy huge numbers. All right, given a linear equation, the remaining helium reserve are T in years since 2010. Well, this is fantastic. Since 2010, well, that is the starting point in 2010. So that's your Y-intercept. And we have slope, so I think we're done. So part A, the helium reserve is depleting 2.1 per year. I'll use T, because it says right here to use T. And they started with 16 billion cubic feet of helium in 2010. So for part B, in 2015, how much will the reserve have? I don't know. But I know in 2015, that is 5 years later, so we're going to use T equals 5. So negative 2.1 times 5 plus 16. Oh, I think I calculated this one already. 5.5 billion cubic feet. Make sure you label. We're a stickler for that in PreCalc. All right, and then part C, if the rate of depletion doesn't change, when will it be totally depleted? So when will the reserve be 0 is what they're asking. So 0 happens, I don't know, we got to calculate that. So negative 2.1 T plus 16, how many years after 2010? Do a little solve in here, and we find out it's about 7.6 years. So if I think back to what T equals meant, 7.6 years after this would be between two, oh no, it already happened. So we'll say between 2017 and 2018. I don't know if that's accurate data. Usually these math problems are lies, so don't feel too scared about this. All right, when hired at a new job, Selling jewelry, you're given two options. The first option is a base salary of $17,000 with 12% commission, or a base salary of $20,000 but a lower commission. So how much jewelry would you have to sell in order for option A to kind of take over the salary for option B? Because you are going to make more money on option B if you're not a super seller. We got to figure out what that turning point is. All right, so for option A, you are going to earn 12% on your sales. So that's like your rate of change. But you're going to start with $17,000 no matter what. For option B, you're going to earn 5% on your sales. So you're going to start with $20,000. And let's go ahead and figure out where they equal. And that'll tell us kind of the tipping point. So I'm going to subtract 0.05x, excuse me. Oh, jeez. Never seen double decimal points like that. Let's try that. 0.05x. I'm going to subtract 17,000 here. So 0.07x equals 3,000. And we're selling jewelry over the course of a year, so keep that in mind when you determine if your answer is legitimate. I don't really know how much jewelry is legitimate to sell, but well, let's see. So with my calculations, we are coming out to like 42, let's see. So I'm going to say about $42,858. So you have to kind of make a decision as to whether you think you can sell that much jewelry in a year in order to determine which salary is appropriate for you. All right, and then this question, this is a good one. We'll go ahead and do this one. The median home value in Mississippi and Hawaii is adjusted for inflation as shown. We assume the houses change linearly, which isn't really true, but you know what? For the sake of the problem, let's go for it. In which states have home values increased at a higher rate? So basically, we need to compare the slopes between the two. So first, let's calculate the rate of change for Mississippi. So the slope for Mississippi is, let's see, 71400 minus 25200, and then 2000 minus 1950. So 50 years. I could have just written down 50. Oh well. When I calculate that, I got, what did I get? Oh, Mississippi is 924. So as far as labeling goes, that's dollars per year. So we're going to do the same thing, but for Hawaii. So the slope for Hawaii would be, okay, clearly there's a bigger rate here, but let's calculate it anyways. So if I subtract, oh boy, 272,000 minus 7440. Okay, so I already did this, and then I divided by 50, and I got $3,966 per year. So which state has a higher increase rate? That would be Hawaii. If this trend continues, what would be the median home value in 2010 for Mississippi? So 2010 would be, if you start here, 10 years later. So what I'm going to do is I'm going to take Mississippi's 2010 price, and I'm going to increase $924 per year for 10 years. So I kind of did a modified version of slope-intercept form. And when I calculate that, I get 80,640. And then part C says, if this trend existed even before 1950 and then continues after 2000, the two states' median home values will be or were equal in what year? And it says the answer might be crazy. So, yeah, I bet it is. All right, let's figure this out. I want to know when they're equal to each other. That means I have to come up with equations. I just have to make sure that the equation kind of makes sense for when time is starting. So I'm just going to do, I think I'm going to go off of, these are smaller numbers, so I'm going to go off of 1950. So in 1950, Mississippi started at 25200, and then it was increasing 924 per year. If I set that equal to Hawaii in 1950, which is 74400, increasing at a rate of 3966 per year. Okay, that's what I have to solve. Gross. All right, let's subtract 924x. Ugh. You know what, while we're at it, let's go ahead and subtract 74400. Your answer is going to be negative, guys. That's okay. It's going to make sense in a minute. Or not, I don't know. So we get negative 49200 equals 3042. All right, dividing both sides by 3042. And we get about negative 16.2 years. So what that means is 1950, negative 16 years ago, so you got to back up 16 years. So that's between 1933 and 1934. So at that point in time, Mississippi and Hawaii had the same value of houses, but clearly Hawaii grew beyond that pretty quickly. All right, we're going to go ahead and end the lesson there, and I'm sure you have a lovely homework assignment associated with these problems.